Ale ja będę na tym.
Bo on też nie był, on był docelowany. Nadal jest?
Nie, ale na tej konferencji.
A, okej. Nie, ale było w porządku.
To student jest w ogóle bardzo sensowny.
Tak. On przygotował się. Dzisiaj akurat spotkał się z drugim.
No jasne. Nie, ja jestem gościem. To jest chodzi po głowie.
Good morning, everybody.
Our speaker, Lingrui Wang from Fudan University.
Yeah. Okay, let's start. Okay, thanks for the invitation from Professor Anna Stunik, and thanks for Polish Academy of Sciences for giving me this opportunity to give you a talk here. And I'm very happy to be in Warsaw. Okay, let's start our talk today. Today my topic will be about the asymptotic behaviors of the Hausdorff dimensions of the radial sets of exponential and cosine functions. And this is joint work with my advisor, Professor Qiu Yuan. And this work, likely this work is published in this month. I think it will be published this month. Okay, let's start. No, it's not working. Sorry. What happened? Oh, it's working. Okay, let's start with the basic definitions of Behaviour set and the radial set. Now we consider a transcendental interfunction f. Let fn denote the n times iteration of the f. And the Behaviour set is known as the stable set, which means for every point in this Behaviour set, there is a neighborhood of this point such that the iteration on this neighborhood forms a normal family. And the radial set is a complement of the Behaviour set. And especially for the transcendental interfunction, the escaping set is very important. The escaping set defined as the point in the plane on which the iteration of the f tends to infinity. And for this function f, we define post a singular set. We will use it later for defining its hyperbolicity later. But we just mentioned here, this post a singular set denoted by Pf is the union, the closure of the union of the function orbit of the singular set of the inverse of f. Here the singular set defined as the critical values and the asymptotic values. Okay, now here is an example of the radial set of some special exponential maps. Here we choose this lambda need to be a little bit small, such that this function is hyperbolic. And if we zoom in at maybe here, like this strip, we will get the right picture here. And okay. Now for this Hausdorff dimension, we need this radial set. Because by this theorem from Prisky in 1999 and later generalized by Lasser in 2009, we know that the dimension of this radial set is the same as the hyperbolic dimension of function f. Here, function f can be rational or transcendental in type. And with some more assumptions, the hyperbolic dimension of this f will be equal to the Hausdorff dimension of the whole radial set of f. here assumption can be hyperbolic or maybe semi-hyperbolic or maybe other assumptions. We will omit it here. And the hyperbolic dimension of the F is the supreme of the Hausdorff dimension of all the hyperbolic subsets of Julia set. Now, let's see what's the definition of this radial Julia sets. Now, let F be a rational function or an transcendental function. We consider the point that there is a sequence in the orbit of F, and there is a definite distance m. We call it m, such that this on this subsequence of the orbit z, we can always find the neighborhood of z maps to a disk with definite radius, and this is denoted by JRM. And if we take the union of m, we will get the radial Julia set.
Let me comment. This notion was somehow independent and introduced by Lingrui and Wang. Wang prepared to just hardly accessible.
Okay, thanks.
And it came, of course, from Kleiner groups.
Thanks. Okay, now let's return to our exponential math. We denoted the exponential function by a lambda z, by lambda times e to the z. Okay, for the whole Julia set, Macmillan in 1987 proved that this Julia set always has Hausdorff dimension 2 for any parameter lambda. And if this function e lambda is hyperbolic, then Julia set always has planar behaviour value 0. And we know that if lambda is, for example, if this lambda lies on the Julia set, then the Julia set will be the whole complex plane and will have infinity planar behaviour value. Okay. Now, which is the hyperbolic here? Here, the hyperbolic means that the asymptotic value 0 tends to an attracting periodic orbit. Equivalently, here this post-singular set P E lambda is a compact subset of the Fadou set. Okay, because here this exponential always have the only asymptotic value and no Greek values. In the Julia set A lambda, we have the important part, the escaping set. Okay, the escaping set will have it's well understood. We have this following results here. In 1983, Devaney and Critch proved that this escaping set consists of uncomposing many curves, and every curve is called a hair. And later, 5 years later, it's proved that every hair is smooth, is infinitely smooth. And in 1999 here, Kotinski proved that the dimension of the union of all these hairs always have the dimension 2, but if we remove the endpoints of the hairs, the dimension will be 1. So that's the well-known paradox of these hairs. But on the contrary, the complement of the escaping set is proved that it's equals to the radial Julia set and has the richer information of the of the dimension. Here in 2003, Ubansky and Stunik proved that the dimension always lies between 1 and 2. And this gives a counter example that this radial Julia set has the Hausdorff dimension less than the whole Julia set, because we know that the Julia set always has the dimension 2. And 1 year later, this dimension of radial Julia set, they prove that it's a real analytic function of this parameter lambda. to prove these two results, they introduce this z+be lambda, which is the part of the Julia set with bounded orbit. Okay, here this orbit is bounded. And by the method of conformal measures, the radial Julia set and this bounded part will have the same Hausdorff dimension. And in 1999, Kapitschka proved this asymptotic behavior of this d lambda. Recall that d lambda is the dimension of this radial Julia set. D lambda, she proved that if this lambda tends to 0, then it has this following asymptotic behavior. The left side is 2 log log and the right side is log log log. And we notice that the left and the right will have the different converge rate to 0. And 20 years later, Bergweiler and Lingrui proved that actually they refined this result by if lambda tends to 0, it will have the following asymptotic behavior, and this result seems that the left part and the right part will have a very similar behavior as lambda tends to 0. But still, we don't have the same coefficient here. The left is 1/2 and the right is 1. Okay, now what we prove is we will have the same coefficient, and we will get the. It's not how to say, it's not the exact, but actually it's a equation here. We have the asymptotic behavior as lambda tends to 0. We will have this. The first term is log 3 over log 2, and the second term is -1 log 4 log 2, and with some constant here log pi, and with some higher term. Okay. This is our first result. And we will see later that this result can be extended to cosine functions. Okay, now this cosine function we call this family FAB, the A e to z and B e to minus z is the cosine family, which is we follow from the name, I don't know, it's given by Macmillan or, and actually, if this FAB is hyperbolic, we still have the radial Julia set is equals to the Julia set minus the escaping set. And we can see from the picture here that this we will have an attracting fixed point here in the black region, and this is purple here. It looks purple here, and the purple part will be the Julia set. And if we denote by BAB the radial Julia set, the dimension of the radial Julia set, it will be a real analytic function of 2 parameters AB, and use the same method of hyperbolic conformal measures. We can see that the radial Julia set has the same dimension as the bounded part. Here, z+be again is the points in the Julia set with the bounded orbit.
Maybe it is general that if we have hyperbolic component in some set of entire functions dependence on parameters.
Analytic?
Example given by paper by Walter Mayer, special type of.
Because for a rational function, it's
Yes,
general.
yes. So this was quite separated.
Okay, and let's see what we have about the asymptotic behavior of this dimension of radial Julia set. And since we have two parameters here, we always consider the speed of these two parameters tends to 0. Now let t be the larger one and t prime be the smaller one of the modulus of these two parameters. If we have this limit beta, which is 1 minus log 2 1 over t prime over 1 log 2 1 over t, and times log 3 1 over t, and we have the limit beta, and then this dimension of radial Julia set will depend on the beta here, but the affection of this beta will not so large that we always have the first first 1 and 2 terms are the same as the exponential functions. And okay, especially when beta equals to 0, which means here log t 1 over t prime and log 1 over t, they are comparable, then here dimension will given the constant by minus log pi over 2. And if this beta is minus infinity, which means t prime tends to 0 extremely faster than t, then this dimension will have the constant minus log pi. Okay, let's see what we used here. Our method is very simple and famous. We use the iterated function systems by the inverse branch of the exponentials and cosine functions. Okay, what is an iterated function system? Maybe we can just click here and consider an open set, which we have a pairwise disjoint subset of Vj, and we have an analytic functions f, and we have its inverse branch fj, such that these fj are all contracting on the v prime. Here we have a prime here, but it's not so clear. And if these inverse branches are contracting, we call this family is an iterated function systems on some compact subset K. And for this family, we have the unique compact invariant subset denoted by K node. It's called the attractor of this family F. And for the iterated function systems, we can calculate the dimension of this K node by the following topological operation. Here we just choose special potential function by minus d log f prime. So we have this special topological pressure denoted by PD. Following Owen's result in 1979, here PD is a strictly decreasing continuous function of this d. And we have PD is greater than 0 and PD is less than 0 for sufficiently large d. And since these two facts, this PD will have the unique 0. And it's actually it is equal to this dimension of this attractor K node. Here the dimension is the unique 0 of this function PD. Okay, now let's for this
you consider finite.
Yes, it must be finite. For infinity, maybe we can just took a finite sub family and take it.
Sure.
Yeah.
You restricted finite subsystems.
Yes. And that's how we do here for the exponential, because we know the exponential with an infinity many branch.
Directly working with this function.
Yeah.
Easy.
Yeah. And so we just consider these horizontal strips of y 2 pi, and we cut these strips by left vertical line of this real part C, and the right part with real part C prime. And we can see that this Julia set will be always contained in the right half plane with real part greater or equal to C. And we consider a finite family on this rectangle Kn. Here, the real part is between C and C prime, and the image part, how to say it? Lies between the 2n plus 1 strips. And on this Kn, the mapping property of this function E lambda is very clear, that it maps this Kn to an annulus minus an integral on the negative real axis. And if we choose this n to be large enough, we'll see that this annulus will contain this rectangle Kn. Just you can see here in this image. Here we have the rectangle Kn. Here the blue vertical line is this real part equals to C, and the green line is the equals to C prime. And the exponential maps this blue line to this blue circle, to this green line to this green circle, and on this red horizontal line and this line here, always to this interval on the negative real axis. So we can choose the inverse branches of this Lk defined on the interior of Kn, which maps Kn into every strip like Kn intersecting this Sk by Lk. And precisely we have the following expression of this Lk. And then we choose K lies between minus n to n. We find a finite iterated function system on this rectangle Kn. And this system will have an attractor denoted by Jn, and its dimension denoted by Dn. So to calculate the dimension of Dredger Julia set, we calculate the dimension of the Dn. And now Dn is the unit zero of this pressure. Here, this capital sigma has the following form, and so we just need to estimate the derivative here. But we know that the derivative of this logarithm is exactly the 1 over the modulus of this z. And if z lies in the small rectangle Sk intersecting Kn, then we have the modulus greater than some bk and smaller than some ck. So by some computation, the exponential of the pressure is greater than this sum and smaller than this sum. Okay, to estimate this sum of something like alpha k plus beta square and plus gamma of some power, we use.
Do you remind how is capital N related to lambda?
Here, capital N must be greater than.
Okay.
log 1 over lambda.
So, but you consider any capital and satisfying this.
Yes.
Okay.
Yes. And n greater than.
So you have a sequence of.
Yes, we have a sequence of finite systems.
And you need to know that it is really enough to calculate this hyperbolic dimension.
Yes.
Because a priori maybe there are other.
Because we have here, Jn is always a subset of this JBD. And if we take the union of this Jn, this bounded part will always contain in this the union of Jn.
So, and then you use the theorem that
This JBD has the same dimension, yes.
So here is some theorem.
Yes. So to estimate this summation of Ck and Bk, we use the following symbol lemma. We can just obtain this lemma by replace this summation to integrals, and we just go here. So if we choose the special n, which is greater than this a lambda, then we can have the first asymptotic behavior of this dn. Here, kappa is any constant lies between 0 and 1. And actually, we will choose kappa sufficiently close to 1. So we can get the asymptotic behavior here, and actually, here is enough to show the first term of this dn or d lambda has the coefficient 1. This lemma is easy to prove, and the idea is just to calculate the pressure by this PD1 is greater than 0 and PD2 is less than 0. We can see.
So you have this logarithm RC divided by logarithm of 2. Is this analytic at lambda equals 0? I don't think so.
Sorry?
No, I have a question. You gave some you wrote some function. Now estimate and after it's 0. The question is function of lambda.
Yes.
The question is it analytic with respect to lambda or not at lambda equals 0? Clearly no.
No.
So it is different than for c squared plus c.
Yes, but
Yes.
there is no map for lambda equal to 0.
No, but we can ask about how the dimension of Julia set and the parameter c to 0.
Yes, that is also
Yes,
concerned
but,
because there is no map
yes.
lambda x c for lambda equal to 0.
But it actually it's like z plus c as c tends to infinity. This is similar. Because here lambda equals to 0 is a singular point of the family.
Lambda equals 0, we have 0.
Yes.
0 is very strong. No, I just think what is the limitation exists, but there is no continuity.
Yes. And actually,
Nevertheless, my observation and my guess, which is true, is that it's not like for rational maps, where we have even Taylor's series for Hausdorff dimension as c equals 0, and this is known.
yes. Because c equals to 0, we still have an polynomial. So this is analytic in the neighborhood of 0.
Yes.
But here it's not analytic on the neighborhood of
because
0. Yes, because 0 is not on the parameter plane.
Not in the family.
Yes, exactly.
Something developed.
Yes. So we can only ask what's the asymptotic behavior. Yes. I think if I remember, if I'm correctly, there are some results about the projective polynomial that c tends to infinity. They still have some behavior of the dimension Julia set.
This dimension tends to be because it is count-volume which
Yes.
is sparse.
Yes. So use this lemma, we can deduce the following functional equation of the dimension d lambda. See, to prove this d lambda, first we deduce the upper bound of this dn. From dn is less than the summation of ck, and by the lemma of this summation is less than this thing. If we take the logarithm of the left side and the right side, we have the left side is 0 and the right side will be 1 minus dn times log c minus log dn minus 1 and plus some constant. So we can have this inequality here. Dn minus 1 is less than something. And similarly, we have the lower bound of this dn. But here we can see on the lower bound here we have something about the c prime and the n, both c prime and n. So we need to choose some suitable n to estimate this part. And for us, we choose n between a lambda and 2a lambda. So we need this not so large.
What is A lambda?
Sorry, a lambda is
Oh,
here.
it is.
It's something greater than log 1 over lambda, but not so large. Yeah, for this lower bound, if we choose this n lies between a lambda and actually this 2 is not essential. We can choose any constant times a lambda. For this n, this c prime over n to dn minus 1 is tends to 0 as lambda tends to 0. It's not hard to calculate. So the lower bound gives that this thing, and actually we have this dn minus 1 is greater than the same thing. So but we need to say something, because here we have dn minus 1, but we cannot replace dn minus 1 by d lambda minus 1, because for this this inequality we require n lies between a lambda and 2a lambda. So we cannot just let n tends to infinity. But if we put this minus log to the left hand side, and we note that this function is increasing, and so we can replace this x by anything greater than x. So we can replace this dn by this dn lambda, and remove this minus log to the right side. We have this lower bound of d lambda minus 1. And on this upper bound, this n is without any restriction, so we just let the n tends to infinity. We have the upper bound of the d lambda minus 1. So d lambda minus 1 have this equation. Not here. Here, d lambda minus 1 have this equation. So finally, to prove our theorem, it is enough to solve this equation by some iteration of this d lambda minus 1. Just like we show here, we replace this d lambda minus 1 by its right hand side. So we just estimated this thing, and we found that the first term is log 3 and the second term is minus log 2 1 over d lambda minus 1. And so we have the first expansion of d minus 1. And we use this d lambda minus 1 again. We use the second term is actually the log 4 1 over lambda. So we take this by replace this by log 4 1 over lambda. We have the final expression of d lambda minus 1. Yes. Any questions or?
So d tends to 1, yes?
Yes.
Lambda tends to 0.
Yes, as lambda tends to 0, d will tend to 1.
N with n's. We are interested in hyperbola. Sorry. Dimension is 2. Dimension is 2.
This is 2.
Hyperbolic dimension is 1.
Yes, because for endpoints you will have some escaping.
So if you choose n to be equal a of lambda, it gives you that bound from below.
Yes.
And to get bound from above, how do you read the
Yeah. Here n is we don't have any restriction here, so we can just let n tends to infinity.
no matter what its relation to lambda, it's just you keep lambda and push n to infinity.
Yes, yes. Okay. So for the cosine functions, it's similar. So we start with the construction of the system, the finitely iterative function system. And for this function f(a)(b), we know that it has two critical values, v minus and v plus. And we have infinitely many critical points like uk. Here uk maps to v plus, here u0 maps to v plus, and u0 plus pi I maps to v minus. So we can write this f(a)(b) into the following form. Here is a composition of the translation, the exponential, and the function of v plus over 2 z plus 1 over d. So it's the composition of three functions. We take a curve. Actually, it's not a curve. It's a union of an interval and a vertical line, and we consider the complement of this gamma. Maybe it looks abstract, but later we can show you. I can show you a picture. So maybe, and let's see this picture. Here we know that this f(a)(b) is a composition of a translation and exponential and v plus 1 over d. So it maps this vertical line, which passing through the critical points, into this interval, which is this is a critical value and this is a critical value. And if we start from this critical value by a vertical line, here gamma, the orange line can be in the upper half plane or either in the lower half plane. It depends on the image part of this critical value. And this pre-image of this line is are some curves, parallel curves here also in orange. And if we remove these curves and this vertical line, we obtain many half strips denoted by P0k and P1k. Here 0 and 1 are just symbols denoted by just means in the right part or the left part of this blue line. Actually, you can also use other symbols like plus or minus, or I think for this function, should I use the notation ZR and ZL, means left and right.
So then the region P11 is mapped to what?
The region P11,
for example, P11,
here,
yes,
maps to the whole plane, remove
minus,
this minus this interval and this.
Okay, and the region P
maps
is
to
mapped
this.
onto, okay.
Yes. Every half strip, like this is the left part or the right part, are mapped to the plane minus this line. So again, if we restrict the real part of D and we choose the restriction to be large, we will have some here. We have something like rectangles, but not actual rectangles. Here is K plus and K minus, and we take the union of the K plus and K minus is some two rectangles like sets, and the image of these two sets will contain these two sets. So we cut the plane by this C plus, C minus, C plus prime, and C minus prime. Just like this here, this red line is the real part equals to C plus, and this green line, it means the real part equals to C plus prime. And here the red line, the left red line means the real part equals to minus C minus, because here C minus is positive, so we just add the minus here. Also, this green line means the real part equals to C prime minus C prime minus. Here, we can see here and here. And with some calculation, we found every small rectangle maps to this set. It's something like an annulus, but not a real annulus. But it's very close to annulus. We can see by Roche's theorem. It's not very difficult. So finally, if for an iteration function system, we need the contraction of the inverse maps. So we estimate the derivative of the inverse branches, and we found that it is very close to the 1 over W. And this arrow is uniform as this for the parameter, and it's not depends on the position of the point W. So we have another iterative function system denoted by G. Here KQ, we did define here? No. KQ is the union of these two sets. So we have another iterative function system, and it has an attractor Jn tilde, and again it is contained in the body part of the Julia set. Similarly, if we have the limit of this or the comparison of this converging rate of these two parameters, say the limit is beta, then we have this functional equation of the dimension of this radial Julia set JR. And it depends on this beta here. But we won't give a proof here because it's very similar as the exponential. We just have some remarks. Actually, we proved that for the dimension of this JQ, we have this functional equation. If n is greater than b t prime here, t prime means that this n must depend on both two parameters. If n is large enough, then the upper bound always holds for any n. So we can, at n tends to infinity, we have the upper bound for the dimension of radial Julia set. And the lower bound, unfortunately, not always holds for any n. Because if beta is not equals to minus infinity, here, this means the two parameters t and t prime are comparable when they cancel 0. And then the lower bound always holds. This means the left part and the right part are very similar. But however, if the beta equals to minus infinity, this means t prime tends to 0 much faster than t. So we just consider another system because we can just throw the left part away and we just consider the right part from k plus n to k plus n by this L, by the inverse of the function of f a b. And again, we deduce the lower bound for this system, and we replace the dimension by the dimension of radial Julia set. And again, we can show this equation. And I think that's all for my talk today. Thank you very much.
Perhaps I would like to ask about approaching parabolic parameters. So for example, for lambda going to 1 over e, we approach parabolic parameter, and there is a paper by myself and Mariusz Shanghai, we prove continuity of radial of dimension of radial set if we approach parabolic parameter. And then there is another paper by Mariusz and Yomava, and they prove a big kind of estimate of asymptotic of how fast the dimension.
The derivative of the dimension. The derivative of the dimension?
I'm not sure if it's a derivative or something less. I'm not sure if they prove differentiability. But maybe with your method you can prove more delicate estimates of this asymptotic. Have you thought about it?
No, but I remember another paper. I don't remember the author, but I think there is a paper about the derivative of the d lambda as lambda tends to 1 over e. Yes, because as lambda less than 1 over e is a real analytic function, and we have the derivative.
So maybe this is what I explained in Tava. So maybe second derivative, or more delicate estimate.
Differentiability will be helpful because quadratic coordinates will be quick to say that square solution.
What was this?
He gave for quadratic polynomials from inside the Cavier asymptotic. Hausdorff dimension. It's continuous, but it is not.
Yes.
It's not, of course, but.
But similarly, we can ask what's the asymptotic behavior of the derivation.
Maybe as here, lambda tends to something concrete, parabolic, not zero. Maybe the situation will be the same as for the polynomials, quadratic functions. A little bit less precise.
Yes.
Yes, so the question would be, can we prove some parallel results for exponential family modeled somehow on Lingui's approach?
Here it will be harder because we have sequence. We have sequence of functions. That's one. An additional. And discuss. Do something.
What do you think about the possibility of using your approach to this setting?
Maybe. Any more questions?
Some other questions.
Or online questions?
There are a lot of participants, but how to operate this?
They are online.
There is
Are there any online
high-level
questions?
workers that high-level.
Hello.
Would be visible on chart.
Sorry.
Hi everyone.
So are there any online questions?
No, it should be. Oh.
No, there are more participants.
Yeah, there.
There's no questions from me.
Yes, so now you can.
Hello, everybody online.
So you have a question? Sorry.
I don't have.
No more questions? No more questions? Okay, thank you.
Thank you.
Thank you.
Thank you. Thank you. Bye. Thank you. Goodbye.
Dobrze.